press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about modes of vibration in open pipe or open air column. A column of air in which two ends of a cylindrical pipe are open is called an open air column or open pipe, and a cylindrical pipe or tube in which the one end of the cylindrical pipe is closed and the other end is open is called a closed pipe. Now we have discussed about the open pipe. So in an open pipe or open air column, open pipe and open air column, all frequencies are present, very much similar to the vibrations of a stretched string. Here both odd frequencies and harmonics and even harmonics are present. That means the frequencies of overtones are harmonics of the fundamental frequency. Harmonics of the fundamental frequency. That means to say, here F1 is to F2 is to F3 is to etc. is equal to 1 is to 2 is to 3 is to etc. That means here F1 is equal to V by 2L is called fundamental frequency, or it is also called first harmonic, fundamental frequency or first harmonic. Now F2 is equal to 2 times F1. It is called first overtone and second harmonic. Now F3 is equal to 3 F1, that is it is the second overtone and third harmonic. Similarly, Fn is equal to n into F1, so that is n minus 1th overtone. This is n minus 1th overtone and nth harmonic, where n is equal to 1, 2, 3, 4 etc. is an integer. Now when we put n is equal to 1, we get Fn is equal to F1. Therefore fundamental frequency is called the first harmonic, and also remember that even in the case of open pipe, in fundamental mode of vibration, minimum possible number of nodes and antinodes are formed. That is minimum number of antinodes are 2 at the two ends of open pipe and one node between them. So when we go to fundamental mode or first mode to second mode to third mode to fourth mode etc., So one each node and one each antinode increases from fundamental mode. That means in fundamental mode, one node and two antinodes. In the first overtone or second mode or second harmonics, the number of nodes formed are 2 and number of antinodes formed are 3. Right. So here note number 2. So fundamental frequency f is inversely proportional to, right, 1 by 2L I am taking it, right, when 1 by L when V is constant and f is directly proportional to V when L is constant, right. So that means to say the frequency can be changed by changing velocity as well as length. So you might have seen a flute. This is like this. This is an open end and this is also an open end, right. Now here there is some hole like that. Here there are number of holes depending upon the flute, right. So it may have several numbers. Long flute will have more number of, right, holes. Now here we can vary the velocity by blowing the air, right. The person who play the flute, right, he will vary the speed of blow. We know that velocity of sound increases in the direction of wind, that becomes V plus W, right. Just if we blow the air with very high speed, then velocity of sound will increase, and by closing the different holes, right, they can vary the length. Suppose he closes here, then this length will, right, vibrate, or otherwise if we open it, this length will vibrate. So just by opening and closing, we can vary the length, right. This is how, right. And if you put the case of Shahanai, it will be like that, and here at this end we are having some holes like that, and they use some arrangement consisting of white arrangement, but what we call PP in Kannada. By using that, they can vary the speed. We know that from the equation of continuity, right, as area of cross section increases, velocity of flow increases as well as velocity of sound also increases. And here the other end we have given the more space compared to the flute. Therefore, the loudness produced by Shahanai is right less than loudness produced by a flute, because here the particle can vibrate with maximum amplitude or more amplitude compared to that of a flute, and obviously loudness is directly proportional to, right, or loudness depends upon intensity, and intensity is directly proportional to square of the amplitude. So this is how this instrument can work. Now we will take another concept, that is modes of vibration in a closed pipe. Modes of vibration in a closed pipe. Now, a closed pipe is one whose one end is open and the other end is closed. Now, let us consider a closed pipe of length L closed at one end and open at the other end, when a vibrating tuning fork is held at the open end or mouth of the tube, right, the sound waves in the form of alternate compressions and rarefaction travel along the length of the pipe and incident at the closed end. Since there is an obstacle in the path of the wave get reflected. One thing, in open pipe, the reflection is due to the change in pressure, right? And here it is due to an obstacle in its path, right? Now, in case of open pipe, when compression is incident at the other end, it reflects as a compression. Rarefaction incidents, it reflects as a rarefaction. There is no phase difference between incident wave and reflected wave. But here, since the reflection is due to obstacle, right here, if a compression is incident at the other end, it reflects as a rarefaction. Or if rarefaction incident at the closed end, it reflects as a compression. Therefore, in case of a closed pipe, there is a phase difference of pi between incident wave and reflected wave. Now, the reflected wave superposes on the incident wave, forming a longitudinal stationary wave with nodes and antinodes, right? Now, in first mode of vibration, in first mode or fundamental mode of vibration, right? Now see here, at the closed end, the air particles are in contact with the solid, right, and it has a minimum of freedom of vibration. Therefore, a node is always formed right at the closed end. But at the open end, the air particle have maximum freedom of vibration, right? They can vibrate with maximum amplitude. Therefore, an antinode is always formed at the open end. Remember, in case of open pipe, at both the ends, antinodes are formed. But in case of a closed pipe, a node is always formed at the closed end and an antinode is always formed at the open end. So, this is the minimum number of possible nodes and antinodes here, right? So, therefore, here we are having, right, here this is one node, one antinode, and this is a half loop. It is not the complete loop, it is the half loop, right? Now, if F1 is fundamental frequency and lambda 1 is fundamental wavelength, then we have velocity of sound, that is the V, where V is velocity of sound. V is equal to, right, F1 lambda 1 or F1 is equal to V by lambda 1. Remember that in case of a stationary wave, the distance between a node and an immediate antinode is lambda by 4. Therefore, this distance is equal to lambda 1 by 4, which is equal to the length of the pipe, right? So, here L is equal to lambda 1 by 4 or lambda 1 is equal to 4L. Therefore, right, F1 is equal to V by 4L. Let us take it as equation 1. Recall that in case of open pipe, the fundamental frequency comes out to be V by 2L, because where we have taken the distance between two antinodes, lambda by 2L, remember that. Here we are taking the distance between node and antinode, which is lambda by 4, therefore it is 4L, right, and it is called fundamental frequency. Fundamental frequency. Now suppose if we have another mode and the next mode of vibration, so L is length, right. Now this in the next mode of vibration. In second mode or first overtone, the one node and one antinode will increase. So here node is always formed, and here we have another node and an antinode here. So again between two nodes there is an antinode, right. This is an antinode, this is node, and this is antinode, right. So here, so how many nodes and antinodes are formed? 2 node and 2 antinode. So when we move from one mode to another mode, so one node will increase and one antinode will increase, and here this is 1.5 loop or segment. Then if F1 and F2 we will take, F2, lambda 2 are those of first overtone. Those of first overtone, that means frequency and wavelength. Then we will have, right, V is equal to F2 lambda 2 or F2 is equal to V by lambda 2. Now, so here lambda 2 is the wavelength. Now up to here it is lambda 2 by 3. Again up to here it is lambda 3 by 3, up to here it is lambda 3 by 3. That means the length of half a loop is lambda by 4, or in this case lambda 2 by 4. So lambda 2 by 4 plus lambda 2 by 4 plus lambda 2 by 4. So the length is equal to 3 lambda 2 by 4. Therefore here length L is equal to 3 lambda 2 by 4, or lambda 2 is equal to 4L by 3. Now therefore F2 is equal to, remember that F2 is equal to V by 4L over 3, that is equal to 3 into V by 4L. 3 into V by 4L. What is this V by 4L? That represents fundamental frequency F1. Therefore, F2 is equal to 3F1, equation 2. Again here, see, we have already discussed modes of vibration in stretched string and modes of vibration in open pipe. In both the cases, F2 comes out to be 2F1, right? But here F2 comes out to be 3F1. That means it is first overtone, but it is third harmonic. First overtone, it is third harmonic. But in string and open pipe, first overtone is second harmonic, right? That means frequency of first overtone is equal to 2 times the fundamental frequency. But in closed pipe, the frequency of first overtone is 3 times the fundamental frequency. That is the difference you have to be noted here. That is exactly the difference between, right, open pipe and closed pipe. Now again, so keeping this, now in the next mode of vibration, this is the length of the pipe L. Now here, now this is third mode and second overtone, right? Fundamental frequency, next higher frequency, first overtone, then next higher frequency, second overtone. So here automatically see here, we are moving from second mode to third mode. That means there will be 3 nodes and 3 antinodes. Now one node is formed here. Now 2 node, 3. The pattern will be like that: node, antinode, node, antinode, node and antinode. So here the number of nodes are 3, number of antinodes are 3, and this is 2 and a half, right, loops. 2 and half loops or 5 half loops. Here 3 half loops, 1 half loop, second half loop, third half loop. Here first half loop, second half loop, third half loop, fourth half loop and fifth half loop, right? There are 5 half loops. Now here, if F2 and lambda 2 are those of second overtone, then we have V is equal to lambda 3 F3, or F3 is equal to V by lambda 3. Now, so if lambda 3 is the wavelength of the second overtone, then see here, this is 1, 2, 3, 4, 5. So this is 5 lambda 3 by 4. So here L is equal to 5 lambda 3 by 4, or lambda 3 is equal to 4L by 5. 4L by 5. Therefore, F3 is equal to V by 4L by 5, that is equal to, right, 5 into V by 4L. Therefore, that F3, right, this is equal to 5 times F1. In string and open pipe, F3 is equal to 3F1, but here F3 is equal to 5F1. So this is second overtone, fifth harmonic. See here, we have fundamental frequency, first harmonic. Next we are having third harmonic. Next we are having fifth. Similarly, we can show 7, 9, 11 harmonics are present, but no second harmonic, no third harmonic, no fourth harmonic. Suppose if the fundamental frequency is 100 hertz we take, then F1 is equal to 100, F2 is not equal to 200, 200 is absent. Next possibility is 300. Again, further next possibility is 500, 700, 900, etc. But no possibility of 200, 400, 600. That means no even harmonics are present, only odd harmonics are present. Let us take it as equation 3. From equations 1, 2 and 3, we get F1 is to F2 is to F3 is to etc. is equal to 1 is to 3 is to 5 is to etc. Right? That means F2 is equal to 3F1, 5F1, etc. Therefore, in closed pipe, only odd harmonics are present. That means the frequencies of overtones of a closed pipe are odd harmonics of fundamental frequency. Right. Now, we'll take some points. So, in a closed pipe, number one, the frequencies of overtones or odd harmonics of fundamental frequency, odd harmonics of fundamental frequency, that is, right, F1 is to F2 is to F3 is to etc. is equal to 1 is to 3 is to 5 is to etc. Now, that means here F1 is equal to V by 4L is called fundamental frequency or first harmonic. F2 is equal to 3 times F1, that is equal to 3 V by 4L. It is called first overtone and third harmonic. You should be very much careful. In some numerical problem, they will give a closed pipe is vibrating with the first overtone, or he may be given it is the third harmonic. Third harmonic means it is first overtone. But in case of open and closed pipe, third harmonic means second overtone. Remember that one. So F2 is equal to, right, 5F1, that is equal to 5V by 4L and is called second overtone and it is called fifth harmonic. It is called fifth harmonic. Now, in general, the frequency of nth harmonic, right, Fn is equal to, this is 2n minus 1 into F1, where n is equal to 1, 2, 3. When you put n is equal to 1, 2 minus 1, F1. N is equal to 2, 4 minus 1, 3F1. Right, n is equal to 3, 6 minus 1, 5. It is 5F1 and so on. Right. Now, we left with the two small concepts, that is end correction, that is denoted by E. Now, if we consider a closed pipe, when we consider a closed pipe, say of length L, right. Now, in the first mode of vibration, the frequency, fundamental frequency is equal to V by 4L. Right. So, when we calculate the fundamental frequency, right, theoretically using that formula, and when we calculate it experimentally, but it comes out to be slightly less than that. Exactly, it is slightly less than theoretical value. And again, when we consider an open pipe, here also we are having of length L, open pipe of length L. So, here the fundamental frequency F is equal to V by 2L. Here also the experimental value comes out to be slightly less than the theoretical value, and it is not due to the experimental error, remember that, right. Now, why the experimental value is slightly less than the theoretical value given by this formula? It is because when we consider that an antinode is formed at the open end of the pipe, right here, this is node, but actually a true antinode is not formed exactly at the open end, that is at this point, because here again, though the particles have maximum freedom of vibration, but the vibrations are restricted by the sides of the tube, right. Therefore, the true antinode is formed slightly above the open end, slightly above the open end, right. So, this length is called, right, end correction. Right. So, this is the actually true antinode, it is not formed here. Here also when we consider a true antinode is not formed exactly at the open end, right. Above, at the upper half, it is above the open end, at the lower half, it is below the open end. This is the true antinode. Now, therefore, the experimental value comes out to be slightly less than the theoretical value. Therefore, we need to apply correction to this formula, right. Now, here the distance between true antinode and the open end of a pipe is called as, right, the end correction. So end correction is equal to distance between true antinode and open end. But in case of closed pipe, there is only one open end, there is one end correction. But in case of, right, the open pipe, there are two open ends, therefore there are two end corrections. Right. Now, when we consider this one, the corrected formula. Now, this is the antinode and this is node. Now, this distance is actually what? This is lambda by 4. That means L is not equal to lambda by 4. I will take this here. This is L plus E is equal to lambda by 4. Therefore, replacing L by L plus E, this is 4 into L plus E. This is the corrected formula. Here also replacing F by L by 2 into L plus 2E, right? Because this distance is lambda by 2 here. So, here L plus 2E is equal to lambda by 2. Therefore, the formula becomes F is equal to V by 2 into L plus V. And we can show that end correction E is equal to 0.3 times D, where D is diameter of pipe. If D is the diameter of the pipe, then we can show that the end correction E is equal to 0.3 D, right? So, for ordinary use, we use this formula F is equal to V by 4L. When we need to measure the accurate value of a fundamental frequency or, right, harmonics, we need the corrected formula, right? Right. Now, let us derive expression for end correction. Right. Now, let us consider in first mode of closed pipe, right? Say we are having a pipe of length L1 and we are having the first mode of vibration, right? Now, this is E, right, and this distance is, this is antinode and this is node, this is lambda by 2, nice, lambda by 4. So, therefore, here lambda 1 plus E is equal to lambda by 4. We will take it as equation 1. Now, suppose if we go on increasing the length of the open pipe, say for another length L2, so we will obtain one and half loops. This is E, and now this distance is 3 lambda by 4. This is node, this is true, antinode. Now for second mode of closed pipe, right? Now here we have L2 plus E is equal to 3 lambda by 4. Let us take it as equation 2. So we are having an experiment, that is resonance column experiment, to determine velocity of sound at 0 degree Celsius or NTP by measuring velocity of sound at room temperature, where we can increase the length of the pipe. It is because when we take some water here, just imagine that it is an open pipe. When it is one end is immersed in water, it becomes a closed pipe, right? So if we go on dipping the pipe inside the water, then its length decreases. Or if we raise the pipe inside the water, the length of the closed pipe increases. This is how we can get first mode, second mode, third mode, etc. Right? Now this is equation 1. Now multiplying equation 1 by 3 and subtracting equation 2, we get this is 3 into L1 plus E is equal to 3 into L1 plus E minus L2 plus E is equal to, this is multiplied by 3 lambda by 4 minus 3 lambda by 4, that is 3 L1 plus 3E minus L2 minus E is equal to 0, or 3 L1 minus L2 plus, right, 2E 3E minus E plus 2E is equal to 0, or 2E is equal to, when we take this on right side, this becomes L2 minus 3 L1, or E is equal to L2 minus 3 L1 divided by 2. This is the expression for, right, end correction. Here L1 is called first resonating length and L2 is called second resonating length. Right. Now this is free vibration. So when a body is set into vibration and left by itself, it executes free vibration, and the frequency is called natural frequency of the body, right? So when a body is set into vibration and left free, so its vibration are called free vibration, and right, frequency of vibration is called natural frequency. It is called natural frequency. For example, when a tuning fork is set into vibration and held by the stem, it executes free vibration and its frequency is the natural frequency. When a simple pendulum is set into oscillation and left free, the vibration or oscillation is called natural vibration and the corresponding frequency is called natural frequency. This natural frequency depends upon number one, dimensions or size of the body, vibrating body. Number two, elastic property of the body. We see it when a plastic vessel is dropped and a steel vessel is dropped of the same size from the same height, we say that, but steel vessel produces more sound, right, and plastic vessel produces less sound, right. Now here this is a property, and the third one, and of course we know that it depends upon modes of vibration, whether it is in fundamental mode, second mode, third mode, etc., right. And if the amplitude of vibration remains constant, right, then the vibration is called undamped vibration. Remember that we have discussed in oscillation. If the energy goes on decreases and amplitude goes on decreases, then it is called damped vibration or damped oscillation. For example, when we take a simple pendulum, right, tie a thread to a nail, right, and tie the other end to a stone or any object, right, let's set into oscillation, it acts as a simple pendulum, right. If you left free, right, then the amplitude with passage of time gradually decreases and finally it comes to rest. Such an oscillation is called damped oscillation, right. Now, forced vibration. When a body is set into vibration by applying a periodic force, then the vibrations of the body is called forced vibration, right. Then the body not vibrate with its natural frequency, but it vibrates with the frequency of the right applied force. For example, when we take, I will write it, I am writing guitar. There are strings like that. When a string is set into vibration, the string vibrates with natural frequency and its vibration is called free vibration. But the soundboard of that guitar, it picks up vibration and it vibrates to the frequency of the string. That frequency may not be right equal to the frequency of that soundboard. Suppose if you excite a tuning fork and keep at some distance, you will not hear any sound. Then you press the stem of the vibrating tuning fork to the table, then you will hear that vibration or you will hear the sound. Why? Because that vibrating tuning force applies a periodic force on the table. Therefore, the table began to vibrate. Since we know that intensity or loudness depends upon the surface area of vibrating body, as the surface area of vibrating body increases, the loudness increases. When we are having tuning fork producing sound, its surface area is very less. Therefore, we can't able to hear that sound. But when it is pressed against a table, the surface area of the table is more for the same frequency. Therefore, we can hear the sound, right? So, such vibrations are called forced vibration. And another important thing is, now it is the phenomenon of resonance, right? Suppose, let us consider a wooden block with two holes, right? Now, when a tuning fork A of frequency FA is equal to say some 200 hertz, right, is inserted inside the hole, right. Now, when it set into vibration, it vibrates with a frequency of 200 hertz and set into vibration and left free. Then the board also vibrate with a frequency of 200 hertz. Suppose by keeping, if it has no vibration and we have another tuning fork B of frequency say 100 hertz is, right, set into vibration and inserted in the second hole. Now the tuning fork A begins to vibrate. Why? Because this vibration of tuning fork B applies the force F, right, periodic force on tuning fork A. Now what is the frequency of vibration? Now the frequency of vibration of A is equal to, A is equal to 100 hertz, that is equal to applied frequency. Now the tuning fork A is not vibrating with its natural frequency, it is vibrating with applied frequency, as well as the wooden board also, right, block also vibrating with 100 hertz. But here the difference between natural frequency FA and applied frequency FB is large, about 100 hertz. So the amplitude of vibration is very small, we can hardly see the amplitude of vibration. So when I go on increasing the frequency of B applied force, say 120, 140, 160, etc., the amplitude of vibration of A also increases. When applied frequency is equal to natural frequency of the body, then when FB is equal to 200 hertz, that is applied frequency is equal to natural frequency of the body, the body vibrates with maximum amplitude. Maximum amplitude. That is, a rapid transfer of energy takes place here, right? And this phenomenon is called resonance. The phenomenon in which a body vibrates with maximum amplitude when applied frequency is equal to natural frequency of the body is called as resonance, right? Now this principle of resonance is used in our two experiments. One is Sonometer Experiment and the other one is resonance column experiment. Sometime you might have observed that when we are riding the cycle with a particular speed, then the mudguard appears to be vibrating, right? It is because of the applied force, right? So when we hear the sound that when a truck is moving on the road, the window panes get vibrate, that is forced vibration, but it is not resonance because natural frequency of glass is different from the applied frequency. Suppose if they match, the frequency produced by the truck is equal to natural frequency of the body, the glass may break due to vibration, right? And even in case of hanging bridges, the soldiers, right, will not march fast on the bridge. They will disperse while passing through that bridge. It is because when the soldiers will march fast, a rhythmic sound is produced. It's of definite frequency. It is around the natural frequency of the hanging bridge. If their frequency matches with the natural frequency of the hanging bridge, what happens, the bridge began to vibrate with maximum amplitude and it may collapse, right? And dear students, that completes your stationary waves part as well as that entire unit. And even along while teaching this one, I have given all the formulas required, concepts through notes, right? Those are all useful in competitive examination, right? Remember that I have given that what Doppler effect as an example, right? We have derived all that cases, different cases, we have obtained the frequency that will help you in competitive examination, right? So, we have completed successfully oscillation, waves, sound and stationary waves, right? I hope you understand the concept, right? If you don't understand one time, you go through it, right? Because to understand physics, it needs a lot of hard working, a lot of imagination, a lot of thinking, moreover, a very lot of patience. Anyway, thank you very much.